So the next step here is actually figuring out which groups of our predictor variable are different from each other, right? We've got a significant p-value from our ANOVA, from our linear model, and so we know that our null hypothesis is unlikely, that we can reasonably reject it, and that there is some difference in Easting value between the three different artifact types that we have. However, this single p-value from this ANOVA doesn't actually tell us which groups are different from each other, right? It could be that they're all different from each other. It could be that microburins are significantly different from flake axes, and that microburins are significantly different from denticulated and notched pieces. It could be that flake axes are significantly different from denticulated and notched pieces too. However, it could also just be that flake axes and microburins are the same. They're distributed the same, and there's no difference. But flake axes and denticulated and notched pieces are different from each other. So we need to kind of take another step towards figuring out what exactly is driving the significant p-value. Which of these groups are actually different from each other? Your first intuition at this, if you're kind of following along and thinking this through, might be to just say, well, what if we just ran a series of t-tests? Right? A t-test is comparing two different groups. It's a linear model that does that. So what if we just built a linear model or a t-test of the Easting coordinates as a function of microburins and flake axes, and that's one model, right? And then built another t-test that compared microburins to DN pieces, that's a second model, and then a third model, flake axes, to denticulated and notched pieces, right? And then we would have all these different t-tests, and we could compare, kind of base these different pairs, compare the different pairs and see which ones have significant p-values. Those would be the ones that are reasonably driving the overall significant result of our ANOVA. That makes sense at first glance, but actually there's problems with that. And in order to really unpack the problems with that, I'm going to leave R temporarily and show you something, a little comic that will hopefully explain why this doesn't make sense in actuality. So the reason that this idea of just running a bunch of different statistical tests or a bunch of different models on the same data to evaluate these different pairings, the reason that this doesn't actually make sense is because of what's called the multiple comparisons problem. This idea is that actually when you run more than one statistical test on the same set of data, you're increasing the likelihood of encountering a false positive, and your p-values no longer make any sense. This comic here from XKCD kind of explains this in a funny way. In the comic, somebody comes along and says, jelly beans cause acne. Scientists go investigate that. And so scientists start running a bunch of tests, right? They start evaluating that all these different jelly bean colors and trying to evaluate whether they have a relationship to acne. There's no link between purple jelly beans and acne in this panel, no link between brown jelly beans and acne in this panel, and so on and so forth. We've run this a bunch of times, right? 1, 2, 3, 4, 5, 10, 15, 20 different times we're running these different statistical tests on different colored jelly beans and acne, but one of them, in this panel right here, we found a link between green jelly beans and acne. P is less than 0.05. Whoa, a significant result, right? And then, of course, the news reports that green jelly beans are linked to acne. But the joke here is that they're probably not. What this is the multiple comparisons problem in action, right? And let me explain why this is funny, which is certainly the mark of all good humor, having to require an explanation. The multiple comparisons problem, as I said, expresses this idea that when you run a bunch of statistical tests on the same data, your p-values get kind of screwed up. If you recall what a p-value actually is, right? A p-value is an expression of the probability that you would get your data, right, your result, if the null hypothesis were true. If there's actually no difference or no effect or whatever, no relationship, that's the null hypothesis. And your p-value is the probability that you would get your data if there were no relationship. And so in this comic strip, what's happening is they're running 20 different tests on these data, right? Trying to figure out if brown jelly beans predict acne. So acne you can think of as being on the y-axis, it's the response variable, and the different jelly bean colors are all on the x-axis. So you run 20 different statistical tests here, and you find one, green jelly bean, less than p is less than 0.05. But recall that we've run 20 different tests here. A 5% chance of finding a relationship when there actually isn't one is what an alpha value of 0.05 means, right? It means that 5% of the time we're going to hit a false positive. We're going to find something that's not actually real, that it's just the result of stochasticity, random variation. And so this relationship between green jelly beans and acne would certainly need to be replicated a bunch more, because the p-values here are actually meaningless. We've run 20 different tests, and our p-values don't actually mean what we think they mean anymore, right? Your p-value only has meaning at that level of 0.05 if you run one statistical test. Once you start running more than one on the same response variable, on the same y-axis variable, that p-value doesn't mean what you think it means anymore. That's because, right, you're becoming more likely to find a false positive. You're becoming more likely to find that one case where there is actually a pattern, there is an effect, but it's just random. It's not actually real. You've just happened upon something that stochastically has arisen. And so this green jelly bean result is likely a false positive. We'd be making a mistake if we actually started saying, well, green jelly beans cause acne then, because our p-values at this point don't have the same meaning, right? There's a bunch of math behind this where you can actually correct your p-values. That's what we're going to do next. But in this case, right, where you've got 20 different tests, the actual alpha value for a significant p-value in this case is not 0.05, right? That's only if you run one statistical test. If you run 20 tests, your alpha value is actually now 0.0025, much smaller than 0.05, right? So even a p-value of 0.01 is not significant when you run all these different tests, right? You would need to correct your p-value, your alpha values, to account for this. You're creating a multiple comparisons problem. And so this is why we can't just run a bunch of t-tests on our data and assume that when we find the significant p-value from those, that is the relationship that's driving our significant ANOVA result. We need to do something a little bit different. And in order to do that, we are actually going to run t-tests, but we're going to correct the p-values using one of many different methods.